All right, hello, this is the video for section 5.2 in Math 11, Calculus 1, and this is on the definite integral. All right, so we're going to go over just some of the main points of this section. And so let's go ahead and start. So state the definition of the definite integral. Remember that we defined, or we found in section 5.1, the area underneath a curve by summing up the areas of a bunch of rectangles, and each of those rectangles had a height determined by the function. We call that f of x, and here we're saying x star for any x value in each of the subintervals. So the height was given by f of x. The width was calculated as delta x, which we gave a formula for, b minus a over n. And n was the number of rectangles. And we said that this sum was an approximation of the area underneath the curve. And if we took the limit as the number of rectangles went to infinity, then that would give us the exact area under the curve. Okay, so this is what section 5.1 was about. Now, in this section, 5.2, we're going to define the definite integral. You can see the definition down below. And essentially what we need for the definite integral is we need f of x to be a function defined on the interval a to b. And so the definite integral of f from a to b is given by this elongated s from a to b. We put these limits of integration below and above the elongated s. The function that we're trying to find the area of, and then dx, this is the variable of integration. And this is going to be equal to, the definition of this notation is the limit that we just talked about. So what we're saying here is that the definite integral, the integral from a to b of f of x dx, it is equal to, or it gives us the area, and for right now, I'll write the net area between the curve or the function f of x and the x-axis. And so what that notation represents is if you have a function f of x over some interval a to b, the definite integral represents this area, the quantity, the amount of area between the curve and the x-axis. Okay. If the limit exists, the function f of x is said to be integrable on a b, or is an integrable function. Okay, so a couple of important notes here. I'm not going to read this word for word, but the definite integral is a number. We just said that it represents the area between the curve, the function f of x, and the x-axis. Whereas we saw this, a similar notation in section 4.10. Let me write the integral, the indefinite integral of f of x dx we saw in section 4.10, and this represented a family of functions. This was the antiderivative, the most general antiderivative, capital F of x plus c. Okay. And so a little bit more about the notation. The integration symbol is an elongated s. It's replacing this summation notation. Above and below the summation symbol are the boundaries of the interval a and b. And so that's what we see here, a to b. The numbers a and b are x values and are called the limits of integration, sometimes called the bounds of integration, the upper bound and lower bound. The function that is being integrated is in what we call the integrand. And then dx represents that f of x is a function with respect to x. So just like we used to have d dx, the derivative of some function, f of x, that was the variable with that we took the derivative, that was the derivative, the variable that we took the derivative with respect to. All right, and then the notation for that was f prime of x. Okay, so that dx indicates the variable of integration. Okay, so that variable can actually be different. Notice there here we get the integral with respect to x, the integral with respect to t, the integral with respect to u. The most common variable that we'll use is x, but it doesn't really matter which variable you use. Okay, so what kinds of functions are integrable? Can we integrate? In our class, we mostly deal with continuous functions. So here in theorem 5.1, it states that if f of x is a continuous function on the interval from a to b, then that function will be integrable on the interval from a to b. Okay, so if you read this paragraph below that theorem, it also says that a function, even if it's not continuous, if it has a finite number of jump discontinuities, it will still be integrable. So continuous functions are definitely integrable, but even some functions that have jump discontinuities are integrable as well. Okay, so we don't really need to go into all those technical details. Feel free to read that and let me know if you have any questions about that. Okay, so let's go ahead and do our first integral here. Let's read actually a little bit here, this definition. Evaluating definite integrals this way can be quite tedious because of the complexity of the calculations, and they're referring to the previous example. Later in this chapter, we develop techniques for evaluating definite integrals without taking limits of Riemann sums. However, for now, we can rely on the fact that the definite integrals represent the area under the curve, and we can evaluate definite integrals by using geometric formulas to calculate that area. We do this to confirm that definite integrals do indeed represent areas, so we can then discuss what to do in the case of a curve of a function dropping below the x-axis. Okay. Okay, so let's go ahead and take a look at this first integral. We have the integral, the definite, let's say, definite integral from 3 to 6 of the square root of 9 minus x minus 3 squared dx. And if you were in the lecture, this is the example that I left off on. I didn't get to complete it, but we were talking about it towards the end of class. And so let's think about what kind of function this is. So if we let y equal this quantity here, the square root of 9 minus x minus 3 squared, and we square both sides, and then we add the x minus 3 squared term to both sides, we get x minus 3 squared plus y squared equals, and I'll write it as 3 squared. You may remember this from algebra or any place where you studied conic sections. This is a circle of radius 3. The general formula for the circle is x minus h squared plus y minus k squared equals the radius squared. All right, so let's go ahead and graph this thing. Let's try to give an accurate graph. The center of this circle is going to be at positive 3, comma 0. So 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3. Okay, so the center, I'm going to put a little X at the center, 3, 0. And then from that center, if you remember how to graph this, we just go 3 units in every direction. And that gives us our circle. Let's see if we can get a nice circle out of this. Oops, that's not a circle. Okay, so we'll actually just graph. This is technically the top half, actually. So we are only dealing with the top half because we are looking at y equals the positive square root of 9 minus x minus 3 squared. There is also a negative square root, and that would be the bottom half. But since we have the square root being positive, we're only looking at the positive, the top half of the circle. Okay, so the integral, as we said before here, represents the net area between the function and the x-axis. So let's go ahead and shade that area that we're talking about here. Oh, and actually, oops, let me not get too far here. We are integrating on the interval from 3 to 6, which means we want to find the area of just half of this half circle, so a quarter of the entire circle. Okay, so here's the area that is represented by that integral. And so for this one here, we can use geometry to find the area of that quarter circle, and that will be equal to, that will be our answer for the definite integral. All right, so for this first, for section 5.2, we should be able to use geometry to complete all of these. In section 5.3, we're going to give another method for evaluating these definite integrals, but that's, in section 5.3. So the area of a circle is equal to, so the area of a circle is equal to pi r squared, and the area of a quarter circle is going to be, pi r squared. R is 3 divided by 4. That's you want a fourth of it. So we get 9/4 pi. That is our answer, 9/4 pi. Pi r squared divided by 4. Okay, so pretty simple to do that with geometry. Let's take a look at the solution here just really quickly. Yeah, they graph it. Let's see here. The function describes a semicircle with radius 3 to find the integral. We want to find the area under the curve on the interval from 3 to 6. Okay. And they get the exact same answer. All right. Very good. Let's take a look at one more, actually. Yeah, let's take a look at one more. There's a suggested problem here that we could do just to get a little bit more practice. And it says, use the formula for the area of a trapezoid to evaluate this integral. Okay, so the integral from 2 to 4 of 2x plus 3 dx. So for now, we have to graph the function 2x plus 3. Let's see, 1, 2, 3, 4, 5, 6. 7, 8, 9, 10. Okay, let's see if that works. We might need a little bit more. 11. Oops. Yeah, we'll go to 11. All right. So this function looks, let's graph it in blue. 2x plus 3 will have y-intercept of 0, 3. And then a slope of 2 gives us this point. Slope of 2, up 2 over 1, up 2 over 1. Okay. And 1, 2, 3, 4 across the x-axis. So we are integrating over the interval from 2 to 4. So let's go ahead and shade the region that we want. And this trapezoid is what we're trying to find the area of. This area here, I'm just going to call it A for right now, is equal to that. This is what we are trying to find with this integral. So if you can find that area A, you've evaluated the integral. Okay, so the area of a trapezoid, that looks like that. We have the trapezoid has two bases, base 1 and base 2, and a height. And so we'll just use the area of a trapezoid. In class, I think what we did was we broke this up into a rectangle and a triangle and found the areas and added them up. You're welcome to do that. Try that on your own. I'll do the I'll use the area of a trapezoid formula. So that is the height divided by 2 times the base 1 plus base 2 lengths. Okay, so the height of this trapezoid is 2. It's this distance here. So 2 over 2 times the base 1 length would be this length here. And let's see, that seems to be 1, 2, 3, 4, 5, 6, 7 plus base 2 length, that looks to be 11. All right, so whatever this comes out to be, this is 18. And that is our answer. Just to double check it here, I'll find the area of the rectangle. The rectangle is 2 by 7, we said. And so that's 14. And then the triangle has a height of 1, 2, 3, 4. The triangle has a height of 4 by 2. And then half of that, 4 times 2 is 8. Half of that is 4. So 14 plus 4 is 18 as well. Okay, so our answer is 18. And that one doesn't have a solution. That's okay. Well, trust me. All right, so that's how we can evaluate a definite integral. The definite integral represents the area between the function f of x and the x-axis. And I've been a little bit loose with my terminology here. The definite integral actually represents the net area. And so we're going to talk about what we mean by net area in this next portion of the book. Okay, so when computing the area using a Riemann sum, what would happen if the function was negative? In all of the functions that we looked at, we had the requirement that f of x be non-negative. Usually the function was above the x-axis. So if the function goes below the x-axis, then essentially what's happening there is these function values, which are the heights of these rectangles, would be negative. And so the area of those rectangles would be counted as negative. So to find the net area, we would find the area of the rectangles above the x-axis minus the area of the rectangles below the x-axis. So we're going to treat any portions of area above the x-axis as positive, and any area below the x-axis we're going to count as negative. And so here in the textbook, they are finding the area above the x-axis. They're finding the area below the x-axis, treating them both as positive numbers, but then putting a negative sign in front of the areas below the x-axis. And this is what is called the net signed area. Okay, so let's go ahead and take a look at an example of this. Oops. Let's see here. So example 5.9, we want to find the net signed area between the curve of the function f of x equals 2x, oops, on the interval from -3 to +3. Okay. And we can graph this. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6. All right, so our function should look like this. It has an intercept, y-intercept at 0, 0. And then we only care about the function over the interval from -3 to +3. So our function looks something like this. All right. And so we can find the area. We're asked to find the net signed area on this interval. And so let's go ahead and call these A1 and A2. Okay. The area of, or the value of A1, the area above the x-axis, is going to be 1/2 the base length times the height. This is 3, and this is 6. So this is equal to 9. That's the area of what's above the x-axis. The area below the x-axis technically is a positive number since area is always positive. So the area A2 is 1/2 base times height. This is also 9. But if we want to find the net signed area, we are going to count A2 as negative. And so the net signed area is going to be A1 minus A2, which is A1, oops, A1 we know is 9 minus 9, or 0. The net signed area is 0, meaning we have positive area up above the x-axis, but because there is area below the x-axis, and it's counted as negative, those two are, the same in quantity but opposite in sign, so they cancel each other out, and we say that there is 0 net signed area. All right, so we said, so you can see that, yep, that's what they do here. They do exactly the same thing. The integral from -3 to +3 of this function, 2x, with respect to x, is equal to the net signed area. So this integral is equal to, we found the net signed area to be 0, so our answer is 0. Okay, I'm just going to read this little analysis statement here at the end. If A1 is the area above the x-axis and A2 is the area below the x-axis, then the net area is A1 minus A2. Since the areas of the two triangles are equal, the net area is 0. Oh, here's a nice problem. Let's go ahead and take a look at this one as well. This one will go a lot quicker because the graph is already given to us. But it says find the net signed area of the function x minus 2 over the interval from 0 to 6. Okay, so the net signed area is represented by the definite integral. So we're taking the definite integral of the function x minus 2 on the interval from 0 to 6. And so this is equal to the net signed area, which it looks like there's a positive portion here. It's a triangle, so we'll use the area of a triangle, 1/2. The base length seems to be 4 units, and the height here is given to be 4. And then we are going to subtract from that the area of this smaller triangle. Since it is below the x-axis, A2 is below the x-axis, we are going to subtract that area. So we get 1/2. The base length here, it seems to be 2. The height of that, it looks like, is -2. Yeah, it should be -2 because that's the y-intercept. Sorry, that's -2 down there, but the length of this side here is 2 units. So we get 8 minus 2, or 6 units. That is the net signed area. All right. So we also gave an example in class, and one thing we said was that if you want to find the displacement of an object, then the definite integral gives you the displacement for, some given velocity function. So displacement, I'll just write, if you're asked to find the displacement, this is found by finding the net signed area. And the net signed area is what we find when we find the integral of a function. Oops. But if you want to find the distance that an object travels, not the displacement, not the net travel, but the total distance traveled, then that is not the net signed area, but the total area. And to find the total area, we would count all of the area as positive, and that can be accomplished by, let's see, it says graphically it is easiest to think of calculating the total area by adding the areas above the x-axis and the areas below the x-axis rather than subtracting these areas. Okay. To accomplish this mathematically, we use the absolute value function. So that would be found, the distance would be found by finding the integral of the absolute value of the velocity function. And that's given, oops, there. All right. So, yeah, actually, hey, look at that. We are asked to find, in the next example, to find the total area. So total area or between f of x equals x minus 2 and the x-axis. Over the interval from 0 to 6. Okay, so we can graph this function of x equals x minus 2. The graph was actually in the previous problem that we looked at. 1, 2, 3, 4, 5, 6. 1, 2, and then 1, 2, 3, 4, 5, 6. Let's see what we get. 0, -2, and then rise 1 over 1, rise 1 over 1, up 1 to the right 1. Okay, so that's what our graph looks like. The total area we're going to find, let's just go ahead and use our geometry and our reasoning skills. We can find the total area by finding the area above the x-axis and the area below the x-axis. Let's call that A2, and adding those two values together rather than subtracting the negative area. So A1 is equal to 1/2 base times height. And that is 8. And A2 is equal to 1/2 base times height. So these areas are 8 and 2, both positive. And we found the net signed area in the previous example that we did. Looks like this is exactly the same function over exactly the same interval. But now we're asked for the total area. So we are just going to take A1, and rather than subtracting A2, since we're looking for the total area, we're just going to not subtract A2 and add it instead. So that's going to give us 8 plus 2, which is 10. 10 square units. And let's take a look at the example here, the solution. Notice that the graph was not given here, so you should be able to produce this graph, but you should be able to graph the linear function, which we did here. And so they talk a little bit about how to do that in the example. Calculate the x-intercept as 2, 0. And to do that, we set y equal to 0 and solve for x. And so it's important to be able to find the x-intercept because this point here is where the function crosses the x-axis. And so to the left of that, we are below the x-axis, and to the right of that point, we are above the x-axis. So we can calculate those areas separately and then just add them together. So just reading here a little bit more, to find the total area, take the area below the x-axis over the interval from 0 to 2 and add it to the area above the x-axis. Okay. And then they showed how to do that. All right, very good. Let's see, how long is this? 32 minutes. All right, so we'll go through these properties here very quickly, and then we'll finish the video. We'll just stop. Okay, so properties of the definite integral. So we've defined something called the definite integral today, and there's a few properties. Property number 1, the integral from a to a of f of x. We talked about this one in the lecture, and basically the interval is infinitely thin. It's just one value. It's just from a to a. And so if you think about, instead of going from a to b, it's just from a to a. It's just a little line segment. So since the width of that is infinitely small, the width is 0, basically. And so the area over that tiny interval is 0. Number 2, the integral from a to b of f of x dx is equal to the opposite of the integral from b to a of f of x dx. So if you reverse those limits of integration, you get a negative, you get the opposite value. All right, so let's read what it says here. If the limits are reversed, then place a negative sign in front of the integral. Okay. All right, property number 3. How do you, what's the integral, the definite integral of a sum of two functions? Well, this is kind of like the derivative of a sum, or a similar property that we saw for the derivatives of sums. You can just, for the derivative of a sum of two functions, you can just take the derivative of each function independently. For the definite integral of a sum of two functions, you can just find the definite integral of the two functions separately, and then add those two values together. This also applies for the difference. That is property number 4, it looks like. So we won't write it again. Oh, here's a good one. Property number 5. The integral of a multiple of a function is equal to just the integral of the function without that constant multiple But then you can multiply the integral by that constant, and those two are equal. And so that one's kind of nice because let's suppose that you wanted to find the integral from 0 to 6 of like 2x. Well, if you've already integrated x before on the integral from 0 to 6, maybe you've done this one in the past, well, you can just multiply that value of that integral by 2. Right? So essentially it just means you can take out a constant and then integrate without the constant and multiply the constant afterwards. That will be useful for us later. And the last property, this is a nice one as well. Property number 6, it says the integral from a to b of a function f of x dx. Essentially, it says if you have a function, let's call it f of x, and you're trying to find the area from a to b, then rather than finding this entire area, you can actually choose a value c somewhere between a and b, and find the area from A to C, this area here. Find the area from C to B. And add those two areas, and that is equal to, the entire area from A to B. Okay. That's pretty straightforward. All right. And so let's go ahead and take a look at the next example just to apply these properties. I think we got cut off at the end of class and we didn't get to, but it says, use the properties of the definite integral. Use the properties of the definite integral to express the definite integral of negative 3x cubed plus 2x plus 2 over the interval negative 2 to 1 as the sum of 3 definite integrals. Okay, so it says we apply properties 3 and 5. Okay. Yeah, so we can definitely write this as 3 integrals like this. Just apply it to the first of those terms. Consider that a function by itself, plus the integral from negative 2 to 1 of 2x, plus the integral from negative 2 to 1 of 2. So there's 3 integrals there. So, I mean, we've actually accomplished it there. Unless I'm missing something. But it looks like they also applied property number 5, which we can, just pull out the constant and just only apply the definite integral to the function x cubed. Pull out the constant here. And we could even pull out that constant if we feel like it. Even though it was only a constant, we'll just put 1. Yes. Okay, let's go ahead and see what they did there. Yeah, very similar there. All right, and then the last example, this is the last one that we'll do. Essentially, you have the information that the integral of some function, f of x, from 0 to 8 is equal to 10. The integral from 0 to 5 of f of x is equal to 5. And we want to find the integral from 5 to 8 of this function. So we know the integral from 0 to 5 and from 0 to 8. So if I look at this on a number line, 0 to 5, and then 8 is over here somewhere. I know the integral over this region, and I know the integral over this region here, and I want to find the integral over this region here. So you can see that we can just take the larger interval integral and subtract the smaller one, and then that would leave us remaining with exactly what we want. So the integral from 0 to 8 of f of x dx minus the integral from 0 to 5 of f of x dx is 10 minus 5, which is 5. So the integral from 5 to 8 has a value of 5. And that's, let's see what they did actually. 0 to 5. Okay, that's nice. Okay. So they went in they kind of did it a little bit different, but basically said the interval from the interval from 0 to 8 is equal to the interval from 0 to 5 plus the interval from 5 to 8. And I really shouldn't use plus, but I should use, if we're talking about sets, we could say the union symbol. And so since we know the integral over the intervals 0 to 8 to be 10 and 0 to 5 to be 5, and then the remaining portion you can get by subtracting the 5 on both sides. Cool. Essentially the same thing that we did there. All right. So that's where we'll stop this video. Yeah, let me know if you have any questions. Feel free to visit me during my office hours.